Hi, welcome to this video presentation. My name is Gonzalez Silva, and I would like to present the work entitled Active Power Control of Wicked Wind Farms, Compensation of Turbine Saturation, and Thrust Force Balance. This work was done thanks to the Water Eye project that has received funding from the European Union's Horizon 2020 Research and Innovation Program. In a wind farm, we can have either of the two objectives. The first one is the maximization of power generation, or the second one, which is tracking the time-varying power reference. In this work, we're going to focus on the second problem, which will deal with the real-time power tracking problem. In order to meet electricity demand from a city or from industry, we might be able to directly balance the power generated from wind turbines to the power consumed by the grid. The process is controlled by the transmission system operator that aims to keep the power balance. However, in wicked wind farms, as illustrated in the figure, we have some challenges. The first one is the interactions between wind turbines. Such interactions can saturate turbines, meaning that the available power is lower than the required one in specific turbines. And also, they can increase loads, leading to the second challenge, where a non-uniform degradation might be observed inside the farm. Because of wake effects, induced loads may lead to immature structure failures, as illustrated into the figures. The failures can be either into the blades or into the tower structure. In this work, we have the three goals. The first one is to track the time-varying power reference in the presence of wake effects. Because of them, we might not have available power into specific wind turbines. Then we have to guarantee the power tracking into the whole wind farm. The second goal is to take also structural loads into consideration, because whenever there is available power into the whole wind farm, we have room to look for the turbine loads. However, the two previous goals might conflict against each other when we make the controller, especially when wind speed decreases. Then we would like as a third goal to perform a controller without conflicting with the previous ones. As the contributions on this work, we have the following ones. First, compensation of turbine saturation is achieved, where we can compensate the power losses by the controller. The second contribution is the thrust force balance, where we generalize the wind farm as a whole body working together to distribute the loads among the turbines. And the third contribution is to solve the conflict between the two goals. We have implemented then possible solutions to solve the problem. Here is the proposed framework. At the bottom, there is the power tracking control loop that compensates turbine saturations, where the power arrow is calculated and distributed among the other turbines. We have assumed that each wind turbine is a pure time delay system in which the power measure is approximately to the demanded power from a step before. Then we can design an integral controller to converge the power tracking arrow to zero. At the top, there is the thrust control loop that balances the thrust forces, where we can calculate the mean of the thrust forces of every turbine and their arrow between the current thrust forces and the mean. Then, by an identification procedure, we can tune an integral controller to converge the thrust arrows to zero, which balance the thrust forces then. However, whenever turbine saturation occurs, the thrust balancer will unsuccessfully try to boost the power of saturated turbines, and it will conflict with the power tracking loop. Then, in our approach, through the matrix capital W, we can remove the saturated turbines from the calculations of the mean thrust forces. We can visualize at the wind turbine level, when the demanded power is lower than the power grid, the turbine is considered non-saturated, which the power grid here represents the maximum amount of power that the wind turbine can extract by the wind in a special condition. Therefore, we can track the power demand as a near perfect tracking system. Otherwise, when the demanded power is greater or equal to the power grid, the power mentioned would be exactly the power grid. So there might be an error generated when turbine saturation occurs. The error would be the demanded power subtracted by the power grid. And this error can be redistributed among the other turbines that are not saturated. At the thrust control loop, we can see how the capital W matrix is built, where it depends on the status of the turbines into the wind farm, which are either saturated or not. The switching mechanisms can be proved that it is still stable for each possible values of the matrix W. However, as expected, balancing the thrust forces to their mean value is a marginal stable problem, but as each individual turbine controller are already stable, the stability is still maintained with the integral controller in the simulations. We have used large edge simulations with the simulator for wind farm applications SOWFA, which provide us high-fidelity simulation results to validate our concepts. The high-weighted conditions were set as illustrated by the 9-turbine farm with 5 MW reference wind turbines. We will analyze only the first column of the turbines because the other columns have present the same behavior. The two distinct scenarios can be obtained in the simulations. The first one is with enough available power in all individual turbines. Then we can balance the thrust forces without any problem. The second scenario is when there is enough available power into the wind farm, but not in all individual turbines. Then we can compensate turbine saturation and restrictively balance the thrust forces. As a first result, we have successfully balanced the thrust forces inside the wind farm. Even though the system is not compensating any power, because there is available power in all the turbines at approximately mean wind speed of 13 meters per second, we can see that the thrust control loop converts all the thrust forces to their mean value, using only the appropriate individual power reference set points. Therefore, we can avoid structure overloading of specific wind turbines. For instance, the turbine number 7, we can see a significant reduction of thrust forces using the thrust force balance. Also, the power reference into the total wind farm is kept tracked while we balance the thrust forces. Still analyzing the same simulations, using the thrust force balance, we can see that the individual power demand in light green is followed by the power measured in blue, and at the turbine 7, it is reduced compared to the power reference in yellow. This reduction follows the reduction in the available power in red. This means that the turbine saturation is avoided using thrust force balancer, which improves the trade-off between the demanded and available power. Finally, we have the scenario at mean wind speed of approximately 12 meters per second, where even though thrust force balance is achieved, saturation occurs with the proposed time-varying power demand. At around 550 seconds, saturation occurs in turbine 7, as you can see, and the compensation starts to happen, keeping the total power tracked, while the thrust forces are only balanced on the unsaturated turbine. Once the turbine number 7 becomes unsaturated again at around 950 seconds, the thrust balancer incorporates the turbine 7 again. However, because of the inertia of the rotor and the sudden power availability, a spike on thrust is observed by a sudden pitch blades by the wind turbine controller, which could be fixed, improved by the transition regions, or applying the derivation term on the pitch controller at the wind turbine level. However, despite of this spike, that further research should be conducted, the power demand is in the total wind farm is still tracked, and there's no problem into the concept of power tracking. Therefore, we can have the following conclusions. First, the thrust force balance can be achieved as demonstrated in this work, and it is also beneficial to avoid turbine saturations. Second, the adopted simple strategy avoids the conflict between power and load control goals as we were expecting. Further investigations indeed need to be conducted at the wind turbine level to prevent the observed spike in thrusts, because it's not beneficial for loads in that sense. As future works, we would like to not only compensate turbine saturations, but also compensate turbine failures or any kind of turbine faults, where the turbines is operated under the regular operations. Also, to prevent such a failures or faults, we can, based on the healthy status of the wind turbine structure, limitate the loads onto the turbine. Therefore, we also have to compensate of these constrained turbines. Saying that, I would finish my video presentation.